Next, we want to move on and do the electric field due to this conducting plane. Now, there's two schools of thought we can follow with that, and two different Gaussian surfaces we can go with on this. So I'm going to describe both those Gaussian surfaces in this video, and then I'll probably solve one of them in this video and then solve the other one in another later video. So we might be getting more videos today than we expected. There are two Gaussian surfaces that make sense, and there's things we need to talk about with the charge. In this video, I said that this plane had total charge plus Q. Okay. Well, I'm going to say the same thing for the conductor. This plane also has total charge plus Q. The difference is that in the insulating case, that total charge is spread like in a single line, a single stretch of charge. In the conductor case, I'm going to treat this as though this metal plate actually has a top surface and a bottom surface. So I'm actually going to give it a little bit of a thickness. And so that's important because it does a couple of things. One, since it's a conductor, it says that in between the walls of the conductor, this electric field's 0. And we've established that pretty well in our class. But two, it says that total charge that is plus Q on there isn't in a single line. It's got like Q over 2 on the top and Q over 2 on the bottom. Okay, so I'm going to kind of note that here. The charge on the top is plus Q over 2, and the charge on the bottom is plus Q over 2. Now, when I kind of worked this out on paper ahead of time, I didn't ever write out that total amount of charge on the top or bottom is Q over 2. I don't think you have to pay attention to it a lot, but you have to think about where the charge is as you're drawing your Gaussian surfaces. And this will become more clear as we finish this video. So one possible Gaussian surface you could draw would be a Gaussian surface that goes through the middle of the conductor and then extends out here. Because the electric field, due to this plane, would be this way, on this side of the surface. And it would be this way here. I should be spacing all these above and below equally, but not doing quite so well with the pen. And really important about Gauss's law, remember that Gauss's law is all about the electric field due to all charges, not just those enclosed. So even though the net flux depends on charge enclosed, the field that we calculate is due to all charges. So when we calculate the electric field by looking at the flux through this surface, it's the field, let's say up here, that's due not only to these charges or the portion of these charges that are enclosed, but all these charges across the top and all the charges on the bottom. And again, that's going to make more sense as we keep doing this. Okay, the other Gaussian surface we could explore with this is a Gaussian surface that's a lot like the one we just did, that goes above and below that conducting plane. Okay? Now, if our math is legit, and if our methods are legit, since we're trying to find the electric field at a similar location, we should get the same result, no matter which Gaussian surface we use, provided that those Gaussian surfaces are valid Gaussian surfaces to use. Well, they are. They both meet all our criteria. E is either parallel to dA at each point or totally perpendicular, so there's no flux through there. That works. The area of either this red Gaussian surface or the green one is easy to calculate. Yep, that works. And then E is going to be constant or 0 at all points on there. Yep, E is going to be constant here. I shouldn't say constant or 0, but I should say constant on the portions that have flux through them. Well, yep, across here, and across there, and across here, and across here, E equals 0. Dang it, I shouldn't have said E equals 0. I mean, E is constant. Whereas on the sides here, well, there's no flux through there, so we don't care about that. Okay, so what I want to show is that no matter which of those two Gaussian surfaces you choose, the red or the green, you're going to end up with the same answer. You're going to end up with the same electric field. And it's actually going to come out to be this same thing too. So conductor versus insulator doesn't actually make a difference. Okay, so that'll separate the difference between memorizers and people who actually understand what's going on with this. So let's do this for the red E field. So all the writing I'm going to do in red goes with this red Gaussian surface. Okay, so I'm going to say that integral of E dot dA is equal to the net flux through our Gaussian surface, which is equal to charge enclosed divided by E0. Okay, again, I could break our surface up into 3 segments. I could do E dot dA for the top, I can do E dot dA for the bottom of that red Gaussian surface, and I can do E dot dA for the sides. And I should be putting little vector arrows over all these. And notice how I didn't make these closed integrals anymore because they're not, these three add together to this closed surface, but individually they're not closed surfaces, not closed 3D shapes. Okay. Looking at the dot product on these, on the sides, E is totally perpendicular to dA, so that's 0. And on the bottom of my Gaussian surface, that's inside the conductor. We know that E inside the conductor is 0. So really, I'm just looking at what the electric field is there. That's what this is going to help me calculate. Well, E is parallel to dA, so the dot product part's taken care of. E is going to be constant across this surface, so E you could pull out of the integral, and then the integral of dA is just A. So this just becomes E times the area of the top of my Gaussian surface equals charge enclosed over E0. The area, or the charge enclosed, is the other piece I want to take a look at. So I'm going to make a proportion. Okay, the total charge on my entire Gaussian surface, on this whole thing, is plus Q. If I just want to look at, the total charge on the top surface, then I could call that Q over 2. What I'm going to do, though, I guess, is just call that the charge. I'm just going to keep plus Q as the total charge on the whole surface, and this A is the area of the entire surface. Okay? But as I'm comparing this surface area to this surface area that had charge on it, if I called, in my previous problem, if I called this area A, I have to call the area that charge is on in this problem 2A, because this plane and this are the same size, but I have charge here and I have charge here. I'm spreading this charge out over twice as much area. So my area here I'm going to call 2 times A, where area is, or A is this top surface area size. So the total area that this charge is spread out over is 2A. And that's going to equal the charge enclosed over my area enclosed, where the area that I'm enclosing that has charge on it is just this little area right there. Okay? So let's plug in some stuff. This says that E times the area of the top is equal to charge enclosed over E0. Solving this for charge enclosed, I'd get plus Q times area enclosed over 2 times the total, times the surface area of the top portion of this, because this A, again, is the area of that top portion. Well, the area enclosed that has charge on it, this little area, and the area of the top of my Gaussian surface, this little area, those two are the same exact areas. And so I'm left with the fact that, oh, and I forgot an E0 as usual. And so I'm left with the fact that E is equal to plus Q over 2E0A, which is exactly what I had before, and I could write that as sigma over 2E0. So conductor versus insulator so far makes no difference in my answer, and it shouldn't if I've got the same amount of charge creating an electric field. Okay, that was for Gaussian surface 1. Gaussian surface 2 would be the green part, but I'm going to make that in another video.